So hi everybody, my name is Scott Stetzer and I'm the strategy lead for the software-enabled Flash project. And I'm really happy to see everybody here today. Who attended the keynote and listened to Eric talk? Who joined us for the Birds of a Feather last night for that scintillating conversation that we all had together? 2, 3. No, you don't count. Anyway, how many of you guys here, this is the same question I asked last night, but since I only had 2 guys, how many here are active developers? Who actually writes software? Excellent. So, not that we have the sign, but this is the Storage Developers Conference. So it's really great to see developers show up and talk to you guys. And what we're talking about, software-enabled Flash, is basically software-defined Flash. So we'll talk about what it is and what the project is. It's an open source project, what the unique software components and the unique hardware components are, and how it's focused to meet the needs of you, the developer. All right? And then a little bit of show and tell time. In this case, show and tell is going to be pre-recorded videos of the actual hardware working and running. Thank you, sir. My potential ecosystem partner there is showing some great enthusiasm. Sean, do you want to wander this around and let people actually put hands on it? So that is good news. We actually have, it's the first fully compatible SSD that supports the software-enabled Flash API. And we've got sufficient numbers of these as samples that we're going to be enabling people to borrow these. We'll have a loan agreement, and we're not going to be charging for them. It's 32 terabytes of storage, so it's kind of expensive. But it's 32 terabytes of QLC storage that we'll loan to developers that are really interested in starting to work with this new API approach. Okay, so this started, a number of years ago. We went out and talked to a lot of the cloud guys specifically, and then a lot of the enterprise and a lot of the innovative storage developers, and said, what are you looking for going forward? And we got a whole list of things that people wanted to be able to do with Flash that they're not doing today, what they were looking for in the future. A few years later, we're now in the future. We've listened to all of that. We've incorporated those questions, those desires, those asks into the API, and now into this drive where it's all working together. The hardware and software are now working together to deliver something to you that you can start to do development work with. Okay? So this next evolution of Flash is moving Flash from a drive paradigm, right, into a software-defined paradigm. And our logo. So what does this mean in terms of capability? So a lot of the things that have been asked for by everybody, now everybody had a different approach to how they wanted to deploy this, but they've all asked for the ability to do data placement all the way down to a very fine-grained layer, right? How do they isolate workloads? How do they isolate tenants who have their own workloads from other workloads so that I/O doesn't interfere with everybody else? The big one everybody's talking about these days, of course, is how do I reduce write amplification? Okay? And the big one, especially so many years ago, was I need to be in tight control of my latencies. I need to deliver quality of service to my customers, and I need to be able to define how latencies work. In order to achieve these expectations and capabilities, there's a whole list of other ones, but these were always the consistent ones. The ability to get to some of these capabilities, of course, is the ability to manage queuing within the drive. I/O time, how much reading, how much writing, how they're queued up. Die time I/O prioritization, in control of the flow of the data into and out of the drive. The ability to take protocols and customize them and change them and make them completely unique for new use cases. And of course, everybody came up and said, listen, I want it in open source. I want to be able to pick it up. I want to be able to work with it. I want to be able to change it and customize it any way that I see fit. So please put it in open source. So a little bit about the OSS project. Thank you. We're signed up and we're governed under the Linux Foundation. Of course, Linux Foundation has Linux, so it's a good place for us to be. All of the requirements of the Linux Foundation as a project are in place. So we've got a governing board and we've got an open technical steering committee meeting. This is a good thing because basically the whole project runs out of the technical steering committee meeting. Not for the governing board, but the technical steering committee. Pretty much runs the project. And that's where all the developers get together and say, this is what we need it to be. This is how we need it to work. Of course, the whole purpose of being open source is to make the source codes open, available, and free to download. That is coming soon. As a matter of fact, we're finishing up the last bit of regression testing on the API and the SDK with this hardware that you see here. And then, of course, it's designed for multiple implementations. Not only for you, the developers, to do multiple implementations for how you need it to work, but also multiple implementations from the standpoint of who the vendor is going to be. In this case, in our industry, we know nothing ever works if it's single sourced. So being able to get drives, SEF compatible functional drives from multiple sources is very key to make this project successful. So it's completely open. The whole reason for being an open source, the whole reason for being part of the Linux Foundation is that creates this vendor neutral location where everybody can get together and say, okay, we can collaborate now on building these devices to the benefit of you, the developer, and the industry. Okay. And I do notice we have a few of our ecosystem partners in the room. Thank you. So here is the information that Linux Foundation always asks us to put up. And this basically is saying, yes, the Linux Foundation is purposed not only to supply the location to gather the open source codes from, but to become that vendor neutral, safe place for everybody to work together successfully. Standard statement, I'm not going to read that. Okay, so what is in the hardware? The API specification is up on the GitHub already. This defines what needs to be on both sides of the equation, what's in the hardware, what's in the software, okay? What it amounts to is an industry standard controller. The industry standard controller that we're using today actually comes from Marvell. My Marvell partner is here. Marvell is a member of the foundation already, or the project already. Thank you very much for doing that, by the way. But membership participation is open as well. You don't have to be a member. You don't have to actually join as a member to participate. It's open source. Of course, anybody gets to join. Come to the TSC meetings, no cost. But for ecosystem partners, for anybody else involved, membership has privileges, okay? The controller from Marvell, as you can see, is a fairly standard approach to a controller. The key here is note that the flash is not called out as a specific protocol, whether you're using ONFI mode, whether you're using toggle mode, whether you're using any other modes that we haven't discovered yet. It's completely agnostic to whose flash you're going to use and deploy. So any vendor can come in and join. It's configurable in a lot of different ways. So of course the flash technology, whose flash you're going to use, what type of flash it is, MLC, TLC, QLC, with PLC modes enabled, what flash protocol is going to be used, how much DRAM do you actually put in the drive when you deploy it. So the API specifically states that the DRAM implementation is completely flexible. You can put the standard amount of DRAM on the drive, you can reduce it down to 0. We've got a couple of customers that have asked us, or told us, we don't like stranded DRAM, it costs money. We would prefer not having any DRAM on the device. And we've got other folks that are saying, listen, I don't like using host DRAM, so put all of the DRAM that you need on the drive. The API, the hardware design is completely customizable depending on what drive you're going to build for your customer base. Okay? Form factor, of course, the E1L is the first samples we're doing. The next version is going to be a U.2 form factor. But again, any form factor is possible. You can make a triangle, you can make a circle, it's a PCB, right? Okay, also, targeted hardware features, things that need to be built into the hardware and the firmware of the hardware device itself is those queuing modes. And I will show you the defined queuing modes in a later slide. The ability to do flash abstraction and management, this is key. With the API and with the command set, you, the developer, should not have to worry about how the flash is changing at the drive level because it's all abstracted from you. The drive itself should be able to handle all of the low-level flash functionality, how to program it, how to erase it, what the voltage levels are, what the timings are. This is all really low-level flash management details that differ from vendor to vendor, differ from type of flash to type of flash, and even change over time as you move from one generation to the next, to the next, to the next. But you, the application layer developer, shouldn't have to worry about these differences. So the API is designed to handle that within the drive hardware. Each vendor can build and deploy that drive to use its flash to the best of its ability, and you don't have to worry about how that actually happens. So you can focus on the upper layer programming to make that storage application work properly, and the drive can take care of how to write, read, and maintain the health of the flash to the best of its flash's necessities. Low-level hardware partitioning and isolation. This means we can go down through the API and through the CLI, the command line interface, and define for you how to split up the flash die in the drive. Get complete hardware isolation for different sections of the drive if you need it. Okay. And then some additional acceleration features that should be built into the hardware as well. One of them is a copy offload. This is the ability to send a map of valid blocks to the drive and say, listen, you take care of moving the data around so we don't have to garbage collect in the host. Okay? You don't have to use the PCI bus, use memory on the host, scatter, gather, and then re-rate back to the device. You take a map of the block locations and say, this is good, this is good, this is good, move it. And the drive will take care of all of that transition without moving any data in and out of the host. And it's very efficient and faster doing it that way as well. This is a programmable feature. You can turn it on and use it, or you can decide not to use it and still do it in the host if you so choose. The other benefit of this copy offload feature, right? Garbage collection is the primary thing that we thought of first, but there are a lot of other use cases for this copy offload feature. If you're doing database compaction, a great feature for that, right? What's the other one we were thinking of? Log structured databases, moving data around. And there are a few other examples, but I'm having a senior moment all of a sudden and not remembering. So unique software components. So again, it's hardware and software working together. So what's on the software side? So the open source API is available today. It's the definition of what happens in and out. There's a header file that defines all of the structures and the functionality in there. That low-level API function talks to that higher-level SDK working from the bottom up. The SDK is going to be published very soon, along with us readily handing out samples of the hardware or loaning out samples of the hardware. Within the SDK, you're going to get a variety of tools, not just the source code, but a variety of tools. The command line interface is the first one, the CLI. This is where all of the device orchestration happens. How do you define what the drive needs to look like when you plug it in and use it with the host, right? How do you want to break down the flash die? Do you want to use the entire drive as one device, or do you want to break down the flash die all the way down to individual die as separate devices, virtual devices? That CLI has a Python interpreter in it. So it's completely designed to be scriptable and automated within the cloud environment or the user management environment. FIO test tool, I think everybody here who's ever worked with storage knows what FIO is. Is this correct? Yeah. We have a port so that you can run SEF devices natively on FIO. The good news about that is you can pick up the device, you can pick up the code, and you could start testing the device immediately without actually having to sit down and write a line of code. The ability to pick up and start testing right away exists between the command line interface to set it up and configure it, and then the FIO tool to start running workloads against it. Okay. We have a full set of virtual I/O drivers. This is the protocols that you might want to test, experiment, customize, and deploy. This would be a regular block mode, like any standard SSD, of course, is expected and standard. But we also have the drivers that will deploy an SEF device as if it's a ZNS drive or a FTP drive. As a matter of fact, there are actually 2 flavors of FTP that we're aware of today. There might even be more. But we support both versions of FTP as they've been requested by the 2 different participants in the FTP activity. The nice thing is, again, it comes with source code. So if you're looking at it, you like FTP or you like ZNS and that's your starting point, when you're ready to do something else with it or you need to customize it to your own application, the source code's there. You can start to make modifications, test and see what works, and expand the capability from there. Okay. Also included, of course, a flash translation layer. The FTL is an important part of any deployment of a storage device. So we include a reference FTL. It's in a modular format, so you can pick up portions of it and use it, or you can look at how it's implemented within the reference FTL. If you have your own FTLs already, and all you need is an example of how do I do this on my own FTL, you'll have those examples in source code to reference. In terms of the SDK and the source code itself, BSD license, BSD3 license, this is, as far as I'm led to understand, the most permissive license available in open source. Basically, it says, here's the code, pick it up, go ahead and use it. Now, of course, as a project, we like to see whatever modifications you've made. If they're useful, please contribute back to the project. If you find bugs, send us a patch, we'll fix it in the code and make sure it's available to everybody. But the BSD3 license for all of the source code files, most permissive and allows you to pick it up and use it in any way you want. C language based, of course. Support for 32-bit and 64-bit CPUs with multiple architectures. So not only x86, but also ARM. Think big endian, little endian capability, also built into the libraries. It's supported on all the modern Linux kernels. As a matter of fact, it says so down here, yeah, using the IOU ring drivers now as an enabling feature. It's event-driven, thread-safe, lockless, completely modular, and again, since it's open source and source code, it's built for you to pick it up and start customizing the code to your own requirements. So what's in it for you, the developer, to pick up and start working with? Okay, so again, a lot of the things that I highlighted early on, complete physical isolation, the ability to specify how you want to physically isolate all the way down to the individual flash die level. So you can take that 32 terabyte drive, use it as 32 terabytes. You can split it in half and make 2 16 terabyte versions. Or you can take that 32 terabyte, split it down to individual flash die and have 32 1 terabyte virtual hardware isolated partitions within the drive, ready to use. Okay? Data placement control goes along with that ability to define down to that hardware layer, right? This means you can take one user's workload, apply it to that one physically isolated location, and another workload in another physically isolated location, and the I/O from one user is not going to step on the I/O from another user. So this idea of noisy neighbors can completely be handled all the way down to the hardware layer. Okay? Write amplification, I'll have an example of this, but the big desire is to get down to a right amplification factor equals 1, right? We've heard about this from the ZNS guys, that's their target. We've heard about it from the FDP guys, that's their target. It's a great target for us all to get to. With this software, you can implement, and the interesting thing is, one method may work for these sets of applications, but not those, but the other method can work for those, or you may need a completely different approach. Again, the ability to get in and design and customize the software to fit your needs to reduce that right amplification are completely in your hands as the developer, okay? Latency outcome controls. How do I manage the I/O going in and out of the drive so I get the latency responses that I need, whether I need the fastest latency or I need a consistent latency with no outliers. That again is completely to your control using the API and the command set. Housekeeping functions and acceleration, again, think of that copy offload feature. And then all of the software-defined protocols available to you to pick up, use, and modify FTP, block mode, ZNS, or any other capability. Okay? I think one of the additional thoughts that I would have on this slide, not only that physical isolation, would be a second layer of capability to isolate at an even finer grain level than the flash die. Flash die are getting pretty big, 1 terabyte per chip. That's a lot of flash. And in a lot of cases, you need a much tighter, much finer grain of isolation from user to user, so we can layer on a virtual software-driven isolation layer. We call it a QoS domain that allows you to break that flash die or that individual block into multiple software-driven isolated sections. And this allows you to further separate that I/O, manage those latencies, manage that data placement down into that virtual quality of service domain. So again, hardware and software working together. So let's talk about how that isolation works. How do you get data placement and right amplification control using that hardware layer and that software layer that we talked about? So again, the hardware function within the API, we call it a virtual device. Die level isolation completely separated physically from flash die to flash die. And then you can group flash die together or you can separate them. Completely user configurable when you deploy the drives, and supports any type of media and abstracts the programming complexity of those media differences. And the additional point that I put in here is you can take, for example, this drive is a QLC drive. You can take a portion of that physical isolated die and say, you know, I don't want to use it as QLC, I want to use it as like SLC, pseudo SLC mode. So instead of having 16 voltage levels within the drive, you'll be having 2 voltage levels. So it programs faster. Our early tests between QLC speed and pseudo SLC speed is almost 10x faster in terms of read and write I/O from that pseudo SLC mode. Okay? Once you've got that virtual device defined, then you can come in and put in that quality of service domain. This is that software definition of further finite scale. This is where you can define your workload level isolation. You can use placement IDs, namespaces. You can separate data by superblock. So once you've defined what the QoS domain is, it can assign a superblock to that particular QoS domain or that particular placement ID. That superblock within that physical location will never be shared with another QoS domain. So it's always isolated at the superblock level. Garbage collection, not across the whole drive, garbage collection within the QoS domain. So one user's data is completely isolated from another one. When you need to garbage collect, it's only garbage collected within that QoS domain, within that particular user. So again, right amplification reduction. You're not getting affected by somebody else's user's data expiring and needing to be garbage collected, intermixed with your data.
Could I ask a question?
Sure.
You're using the term superblock, and yet you have die level isolation. So
yes, sir.
what is a superblock?
A super block is a,
What's the question?
I'm sorry, yes. So the question was, since we're using a definition of die level isolation, what is a super block? Okay. The first and foremost, I'd say that super block is configurable when you define the die level isolation in the QoS domain. So the size of the super block is variable. The super block is that group of blocks that are going to be coming together to define how big the I/O path is. Okay. It is separate from the flash block level. So you could have a 4K atomic data unit could be a super block, kind of small for a block. Or you could pull together like 10 4K blocks and have a 40K super block.
And one of the cool things is this is actually configurable via software. So if you decide you've got like 192 die across your drive, that's too wide of a super block.
Yeah.
It's too enormous. You can say make a super block of 24 high.
Yeah. Were we able to answer your question? Okay. So how does that die level and QoS domain level isolation work? So just a quick little animation for how it pulls together. So here is a 32 die device, right? So defining that hardware isolation says let's group some of these die together and we're calling that hardware isolated zone virtual device 0. And we can continue to go out and define that by defining more and more blocks of die into virtual devices. And the shape doesn't matter. In this case, we've always used sort of a rectangle or a square type of format, but you can break this up and have non-rectangular shapes if you so desire. A little strange, but it is possible. Now, once we've defined these hardware isolated zones, virtual devices, the next step is to come in and say, okay, now let's put on that software layer of definition, that QoS domain. And you can see we put that in there. There's a little more space there, so we could put another QoS domain in there. Or we can go over and we can make that next virtual device and use the entire virtual device as its own QoS domain. And then go ahead and build it out. You can see we can put multiple QoS domains in one place or completely occupy that virtual device as a single QoS domain. We can have lots of QoS domains. We can really break this down into very small sections if you need to. The honest answer is I think most people are going to build one device, one QoS domain with one virtual device, because it will be doing a lot of this at scale across hundreds or even thousands of drives. Yes, sir?
How is quality of service enforced? So it seems that domain 3 and 4 share, for instance, one channel, share the same channel. So how do you enforce QoS between those two domains?
Between the two, I'm sorry, the question was how do we enforce isolation between the domains, is that correct?
If they are vertically stacked, so they share the same channel.
Yes, they share the same channels, yes. That does become a little bit of a challenge, but again, there's a lot of bandwidth across those channels getting to the individual die, so not crossing data from one die to another die in the same place means you can use that bandwidth of the channels and avoid that. Although it is true if you're really busy on QoS domain 3 and QoS domain 4, you are going to have a little bit of a collision there. If physics is physics, you're still stuck with pushing data across those channels.
So, right, yeah, so that means it's fully described that that's what's happening.
That is correct.
That sharing won't happen in some kind of back-end way. Like it's exposed that when you configure it like this, you know that you're doing that thing.
Yeah, so the question was, is it fully exposed? The answer to this is that configuration is fully exposed because you, the programmer, have defined that when you deployed the drive. You know what it is, you know how it's working, you know why you did it that way, right? Yes, sir.
Going back to Mike's question, so in this diagram then, will the super block be striping across all the dies that domain is comprising, or it's a logical concept for the super block?
The super blocks are part of those virtual devices.
What was the question?
Thank you very much. Yeah, so I'm sorry, I always forget to repeat the question. So the question was, the super blocks that are being used, how are they deployed across the virtual devices in the QoS domains? In this case, yes, within the virtual device, the super blocks are all in a pool.
So they are striping across all the dice?
The super blocks are striped across all of the die within the virtual device, yes.
And that is fixed, it's not configurable?
Based on the size that you've defined for the super block, right?
You define that, you choose that when you set this up. So
Yeah.
if you've got it really wide, you can make it as smaller.
Yeah, back to the previous question, it's fully defined by you when you configure the drive for deployment. Now, one of the benefits is, if you're looking at QoS domain 4 and QoS domain 5 in this example, the super blocks are shared within the virtual device underneath this, to the size of the super block. Once QoS domain 4 is assigned a particular super block, only the I/O going in and out of QoS domain 4 will go into that super block. He'll pull it from the pool available to both QoS domain 4 and 5, but once it's been given to QoS domain 4, only 4 can use it. Okay? Once you've actually said, I'm done with that data, and release it, that super block will go back to the pool available to both QoS domain 4 and 5 until it's reassigned for new data. And then it's isolated again to whoever the QoS domain user is. Did I answer your question?
I'm still parsing it, but keep going.
Okay. There was another question back here.
How do you monitor and manage the utilization of all those channels?
That is a very good question. There is a lot of instrumentation built into the API.
What was the question?
I will learn about the end of this presentation that I need to repeat the question. So the question is, how do you monitor the super blocks and the functionality that's built within each of these domains? And again, I think I'd mentioned that there is a tremendous amount of instrumentation built in where you can query all of the statistics and all of the functionality and all of the definitions that are part of this having been set up. Was there more to your question, or did?
It seems like a big management nightmare.
So the response was, it seems like it's quite the challenge to manage all of this. And in some ways it can be, but I believe once you start working with it, those capabilities will be very obvious and actually quite simple to manage. Okay, I think Matthias got his hand up first, and then we'll come back to you.
It's a long question, sorry for that. So for the quality of service domains, I mean, if you split them up in all those small pieces, you're getting like, each of them have a local kind of like your capability of a read and write conflict. I mean, you make it really small, either you can only work on that small part. So there's much higher probability of you having these collisions on the media. So each independent quality of service domain gets a worse quality of service because they have there's a higher probability of writes colliding with the reads. So the question is, I mean, this actually is harmful to split your SSDs into these small pieces because your opportunity for getting a good global, good quality service is kind of like you're working against kind of like the resources that you do have within the SSD. So where does this make sense? Because it is,
Okay.
it's kind of not in,
Yeah. So the question was, when you split up quality of service domains into really small pieces, it can create collisions and actually has the potential to negatively impact the actual quality of service at the drive level. And the question that came out of that, who needs it and how do they use it or deploy it? Okay? In some ways, you're absolutely correct. If you're not doing it for a purpose for your application, then it can be quite a problem. But if you don't need that scale of small QoS domains, then don't deploy it that way. Again, how you set it up, How you configure it, how you deploy it is completely dependent on you, the developer's application, and how you need to use it. Again, I think at scale, when you're talking about hundreds of drives or even thousands of drives, you're not going to break a single drive down into these small pieces. You're going to take a pool of drive and then maybe apply QoS domains there. The example I would use of somebody that actually wants to do this is let's see, I can't mention names, somebody that's actually hosting hundreds and hundreds and hundreds of individual cloud-based virtualized server instances, and they clearly want to get down to a very small deployment on a single user level and have it completely isolated from everybody else. Okay? Yes, sir.
So your virtual device, is that an NVMe endurance group?
It can be, yes.
So if it's not an NVMe endurance group, then can you explain how endurance is managed between these virtual devices across all the NAND on the devices?
It's a good question. The question was,
Can you also
I'm learning now, how do you manage endurance from within each of the isolated QoS domains?
Not QoS domains, virtual.
I'm sorry, from the virtual devices. Again, I believe the answer is that's up to you, the developer, how you want to define and use that. Once you've got it isolated, the flash blocks are going to be isolated within that virtual device layer. Now, you can do your garbage collection separately and uniquely within QoS domains. But you will...
Talking about endurance.
Yeah.
So in your virtual device one, where I isolate these dies, I can run them and use wear them out, and then the rest of the drive, the devices, in their own virtual devices,
Yeah.
still have their own endurance, and I have to manage the wear out of a sub-device.
Yes, that's going to be a challenge for you, yes. You do have the potential to blow out a particular virtual device ahead of the others. Now, the thing that we have been asked for, the thing that this allows you to do is follow that rot in place capability. So if you have worn out a particular set of flash die because you've made it very small and you've really abused it heavily, the rest of the flash blocks are still functional. You can still use them, right? But our hope is that you're hopefully moving workloads around so you don't actually do that to yourself. Okay, no more questions. It's a programmable interface. You can hurt yourself. We try and do everything we can to keep you from doing so. One of the things with the instrumentation that I mentioned before is there will be warnings. When we know there's a problem that's about to occur, it hasn't been saved or you're overusing in certain blocks, we will set up a notification to say, hey, you got to think about doing something here because you're running the risk of wearing me out.
Then what does that do for warranties?
That is a very good question, right? I don't know that we have solved the warranty question completely yet at this point. The question for those of you that didn't quite hear it is, how do you manage warranty in the case of potentially wearing out flash die so quickly? That's going to be, as we get from the POC phase to actually a product that's ready to be able to sell, that's a question that we're going to have to resolve and figure out. And I think in many ways it's going to be some agreement between ourselves and yourselves as the customer defining how that warranty needs to work.
So the counters are all visible, right? All the counters and all are fully visible, so you can actually keep track of this happening.
I'm sorry, I just can't quite hear what you're asking.
The counters of how much you're using each die or each...
Yes. So the question was, how many counters or where are the counters and are the counters complete enough? Yes, there is a lot of instrumentation with all of the counters on the flash die that are there. Okay.
So if you need to, based on all these counters, maybe change the configuration, you can do that.
Once you've deployed the virtual devices, they're not changeable anymore.
So
The QoS domains can,
problem,
yeah.
that's it. I cannot now try to reconfigure
Yeah, once you've configured the virtual devices, you can't reconfigure them. Here, let me go back one. Once these are set up, it's locked, right? Now, if you come in, I'm sorry, I didn't go back far enough. Once you've defined that and deployed it the first time, that's locked. That's not changeable. So the virtual devices, the hardware isolation is locked because of that concern about wearing out flash die inappropriately. You can't intermix them once they've been defined.
But I can lose data and reconfigure it. Or I can copy data somewhere else and then
That is correct. Once you've layered on the QoS domains, these can be reconfigured on the fly anytime you need to. All right? Now, back to the right amplification and garbage collection schemes, if you're spinning up virtual machines and spinning down virtual machines and you put a virtual machine in a QoS domain, you don't have to garbage collect when you destroy that virtual device. You just go say, okay, all of that data is free. You don't have to garbage collect. You don't have to scatter gather.
That in many cases you will understand what's the optimal configuration based on the metrics that you provide.
Yes.
So you don't necessarily know in advance what will be the best configuration. So you can kind of adapt, but that will still require like wipe everything, move it to a different device and reconfigure.
Yeah, so the question is, how do we manage that again, and can we use that as a method to defining when we actually need to move data to a new location to increase the endurance or increase the health of those particular flash die? The answer is yes. Again, that is completely under your programmatic control, and the instrumentation that the drive will send back to you or you can query from the drive gives you all of the information you need to make those logical choices.
Can I keep dies unused, not configured for any virtual device, and then during runtime decide to create these virtual devices? Like reservation of dies?
Yeah, again,
and start using the drive, but then use the reserved dies.
Configuration is up to you. So if you want to reserve die unused until you're ready to actually deploy and use them, you can do that. Okay. Over provisioning is up to you as well within the QoS domain. So, okay.
How do you ensure like even wear out? Like if you have one configuration, run it for a year or two, you wear out like one part of the product.
Yeah.
And then you're like, oh, let me go reconfigure it. And you have like one that's newly never used, and then you mix it with the old, and then you do wear them across that. And you'll get like this.
Not by virtual device. If you've worn out, wow, 10 minutes and I'm only halfway through my presentation. Thank you guys for all the questions. I wish I had awards to give everybody. It's up to you what you're doing and how you're using it, right?
Okay, so it seems that there are some general kind of like configurations that make sense.
There,
you kind of keep them there.
There are. And again, that's the reason. So how do you manage, the question is, how do you manage the wear out? How do you manage the endurance? How do you manage the life of the drive? Again, we're giving you the tools as the developer to be able to manage that from within your FTL. A normal SSD handles that within the FTL. You're in control of the FTL. We've got the reference FTL that you can use for coding examples, or you can write your own FTL. But your ability to get directly to the flash and use the flash is completely up to you, the developer. So you can wear it out, as we've discussed, or you can avoid wearing it out, and we give you all of the tools that you could possibly imagine to help make those right choices. But we can't keep you from actually wearing it out unevenly, okay? We do everything we can to avoid that, but it's still possible for you to write something that will wear something out ahead of something else on the drive. So I have 10 minutes left and we haven't gotten to the demos. Let me rush through this and I will be here all day. Please come and ask us questions offline. The advanced queuing capabilities, there are 3 queuing engines built into the specification and in the hardware. There's a priority queue that basically says, hey, work everything on a priority. There's a fairly simple round robin, handle out all the queues across the channels in order. And the real power comes from the die time weighted fair queuing. This allows you to go set a policy that says how much read ratio I want versus how much write ratio I want, how much priority you want to give to erase functionality going on. And additionally, the ability to go in and say, once I've set that policy and it's running and I'm doing I/O according to the read and write ratios I want, I got a priority write that I have to service right now. And you can move that to the top of the queue, give it the highest priority, and it's going to fire off first. Same with reads. So die time weighted for queuing is a very powerful feature. I'm rushing now, I apologize. Background process controls, we talked about this, garbage collection, using that internal copy offload feature. You set up a bitmap of what needs to be gathered, let the drive take care of it itself. The defined protocol. So here is a TCO advantage that you can realize with a software-defined flash approach. You can buy a set of software-enabled flash devices from whichever vendor can get them to you. Using the API, using the command sets, using your own programming skills, you can then go in and say, listen, I'm running different applications. I can deploy a set of these SDF devices. Buying one source of device, I can run my web apps on this using FTP because I need FTP to run that app. Using the same drive, I've got my streaming app over here on this other box or this other rack, and I need to run that in ZNS mode or block mode. Grab from your pool of drives, add the driver, run it in that new mode. Database app, if you're running block mode for database for performance, I'm sorry, I'm mixing my metaphors here. But the power here is one generic device can be deployed as different protocols depending on what the application requires. And when your needs change, you can take a portion of those drives, run that new application with your completely new protocol or API requirements. The ability is all because it's programmable by you, the developer, and reconfigurable on the fly as you need to within your data center. TCO advantage. Virtual device drivers, of course, you don't need to make changes. They work, the examples work out of the box. You can over-provision per virtual machine in those drivers. You can use any of the protocols. I really want to get to the demos. Here we go, show and tell. Okay, so isolation capabilities. Remember the map and the animation we gave you. I'm going to show you a functional demonstration running on that hardware that we were showing you before. So how we've configured the SEF unit. We've taken two virtual devices. So we've taken a block of flash die, virtual domain A, block of flash die, virtual domain B. On top of that, we put a QoS domain, a single QoS domain on each of those so we can actually start to run I/O. Okay? So we got device A and device B. Let me go ahead and get this started. And we're running two identical workloads using FIO, the patch to FIO. And you can see the read and write ratios are happening here. Blue for reads, orange or red, should be red, for writes. What happens when you turn off the I/O on one device? No impact to the I/O on the second virtual device B. Turn it back in, turn it back on again. You're not seeing the I/O from that one workload affect the other one because you're not intermixing data on those two different virtual devices. Flip it around, do the same thing. Disable and re-enable virtual device B. No impact to virtual device A. A very useful demonstration of that isolation.
You have some shared resources on the drive, right? Like, you have some shared resources on the drive, like DRAM or SRAM. Could you end up impacting one of the virtual devices when you use up all of that SRAM?
The question is, since you're using shared resources, for example, DRAM on the device, can that actually have an impact on the I/O into and out of the flash? Possibly, but I have the feeling, DRAM runs so much faster than the flash does anyway that you're probably not going to run into that problem. And again, we create 8 different pipes for reads and writes and segment that even using the DRAM. So most likely you're not going to see things like DRAM affect your performance either. Okay? And then you always have the option to use host DRAM, especially if you're doing like streams. We've got people that want thousands and thousands of streams. You're not going to do that with the amount of DRAM that's on the drive, so you can use host DRAM and segment that under different memory requirements or memory pools in order to isolate that as well. Can I go through the demos and then talk to all of you guys with your questions offline? I apologize because I got the 5-minute warning 3 minutes ago. Show and tell, so real-time application controlled queuing. This one's a powerful one. So now I'm going to show you how you're going to deal with quality of service domains or workloads within the same virtual device and quality of service domain, right? Using die-time weighted fair queuing. So it's one unit, one virtual device, quality of service domain, read and write happening within that same zone, right? And the key here is showing you how you can set policies and adjust those policies on the fly for changing how the read and write latencies are going to occur. So we start up a workload, it's 50-50. You see the slider on the left. Read and writes are at an equal percentage of die time priority. You go in and you change it, all of a sudden I give more priority to write. So I've got a higher priority on write, which means my write latencies go down and my read latencies go up. Okay? Change it again, make it even higher. You can see the performance is visible on the fly as we've made that request to change the priority. You can flip it around, now give more priority to reads versus writes, and the reads are going to be serviced ahead of the writes according to the percentage that you've defined to it. And again, you can do this all the way down to an individual I/O using that die-time weighted fair queuing capability. I remember on Monday, in this same room, I was listening to one of the cloud people talk about their workloads. And they came through and says, whether it's SSDs, whether it's HDDs, across our hundreds of different apps, what it all comes down to is I've got 60% write activity going on, including the write amplification factors, and 40% reads. That's just how the workloads work. But they came back and said, to us, the highest priority is servicing those reads. I need that read priority, that read latency to be managed and made very small. This gives them or you the capability to go in and say, no matter what the workload is, I want to assign a higher priority to reading, and as policy that will happen. You can get 40%, you can set it to be 80% more priority on doing reads versus writes. So you'll get 8 reads for every write. Not really, but. Last demo is the discussion of how we're going to set this up so you can see it actually we're using a single drive. Again, I don't think anybody's actually going to run it this way, well, except for maybe the cloud service guys with virtualized servers. But we'll take a single unit, we'll leave empty space. I know this was a question of, can you not use particular die? Yes. We'll set up 3 different virtual devices, each with a QoS domain on that virtual device. We'll run one of those domains in FDP mode using a particular workload, using FIO. We'll run another zone in ZNS and another one just using a standard block mode interface. Spin them all up, show them all running separately, and showing them completely isolated. So using that methodology, this is a heat map showing all 32 die that we have. And then we're just going to start them up one by one. You can see one workload is read-only, one workload is mixed read-write, and the third one in the middle is 100% write workload. And again, in order to show that isolation capability, we've kept unused die separating them so you can actually see the I/O differences. So again, not likely that too many people will run this way, but the power and the capability of that programmable API and the ability to isolate workloads at the hardware layer as well as that software QoS domain level is a tremendous functionality that nobody's been able to bring to the industry yet. All capable and within your hands, you, the software storage developer. These demos, I believe, are up on the softwareenabledflash.org website. No! I've just been told I'm out of time, so forgive me. I'm going to keep going. Only one more slide after this. Announcing today, I don't know if anybody saw it, but the announcements went out early this morning, I think 6 a.m. our time. The command set specification has been donated to the project and is now available for download from the Software-Enabled Flash GitHub site. So the API document's been up there for a while. The command set specification, these are the commands that you can issue using the CLI or your own code, are now published and available for you to download and read, including all of the details about the instrumentation. Okay? In addition to that being donated and available for download, I would like to identify for everybody the technical steering committee for the project will be happening this Friday at 11 o'clock. Completely open, you don't have to be a member, you just log in, listen in, ask questions. Any of these questions you've been asking me, if you really want to get a really good answer from a developer, the architects and the developers that are actually writing the code for this API and the source codes for the SDK, they're going to be at that meeting. You can talk to them directly. I would encourage it, actually. You can get that information directly from the softwareenabledflash.org website. Hopefully it's easy to remember, softwareenabledflash.org, one word. And of course the pitch, the call to action, guys, go check it out. Sign up for the mailing list so you can get notifications of what's happening, especially very soon we should be publishing the SDK, the actual source codes. You're going to want to get notified when that is actually available because that's the actual source codes that you can play with. Okay? And of course, for my potential ecosystem partners, please plan on joining the project. Okay? Thank you very much. I know I'm out of time. I will definitely be standing by and ready for questions, along with